morning, everyone. It's so good to see everyone here. I'm so happy to see that so many of you are interested in the same topic that we truly have a great passion for here at Sonat. So just some small practical things. We are going to run the presentation. Questions you can add in the chat along the way. I will ask them in the end of the presentation. So you can also add comments if you want to, and I will share them with Gemma and Christian in the end. You're all muted and we can't see you, so we won't have any interference along the way in the presentation, but we truly like to hear from you in the chat. So I will follow up with the chat. So enough of me. Well, let me introduce to you our experts at machine learning here at Sonat, who will host this webinar. It's the lovely, passionate Gemma Dansk, who is one of the top leading tech in Norway for 2021. And our host, Christian Sloper, who is the fagleder for our top team of machine learning here at Sonat. He makes sure that we are up to date and in the forefront of this technology. So with no further ado, I would send the word over to Gemma and Christian.
Thank you. Yeah, welcome everybody. So our topic of today's webinar is how not to fail at machine learning before you even begin. So the idea here is that we have been doing machine learning for a while, and we have discovered a few things about common mistakes, and we have built up some experience about we feel how you should do machine learning in your organization. Our talk is not very technical. We have aimed for about 45 minutes. But you know, machine learning is not very accurate, so it might go a little bit longer. We'll see. So let's first just present ourselves, since there are so many here, so many of you don't know us. My name is Christian Sloper. My background is in algorithm and complexity theory. And for the last 15 years, I've been doing data engineering in various companies. And last 4 years, I've been doing machine learning in Sonat. I think that's it. And I'm here with Gemma.
Yeah, my name is Gemma Danks, and my background is in genomics and bioinformatics, machine learning and data science. So I have around 13 years of experience of data science, data analysis, and I've been senior consultant at Sonat for the last 3.5 years, where I've worked in with various companies doing machine learning.
Yeah, so an outline of our talk today. So my boss would be happy if we didn't say at least a little bit about Sonat, so we will do that. Then we'll briefly talk a little bit what machine learning is, then spend some time on why you should do machine learning, and then how you can get started with machine learning. And then finally, we have some common pitfalls that we feel that if you know about, you can plan for and avoid. Yeah. So first, Sonat is a IT consulting company with a whole suite of IT capabilities that we offer to our customers. The newest one here is our design company, These Ways. So just want to give a shout out to Hogne and his creative crew. They do UX and service design. But we are here on the bottom left with data science. So we're going to talk, so we do AI, machine learning, optimization, and advanced data analysis. So focusing on that. Yeah, so we've been doing machine learning since 2016. We have collected or gathered a group of, I think, very good people, and our goal is to build the best machine learning environment in Vestlandet. We have a dedicated group for machine learning and data science, so I'm happy to head. Over the years, we have built up a substantial portfolio of projects in various topics like finance, energy, shipping, healthcare, engineering, aquaculture. And we are proud to be the leading AI company for hairdressing in Norway through our work with cutters. Me and Gemma cover some of these topics, and other of colleagues cover the rest. So.
Yeah, so before we get into how to plan machine learning projects and what pitfalls to avoid, we'll first cover a little bit about what machine learning is. So this is just a very basic introduction for those who don't know what machine learning is. So essentially, machine learning is just an alternative approach to problem solving with a computer. So I'm going to use Lego as an analogy here. So you have your Lego bricks, and your the problem is to build some Lego houses out of these Lego bricks. So that's the task to solve. And the traditional approach to this would be to get an instruction manual, which has been created by somebody who has expertise in building Lego and designing Lego and has written out detailed instructions for you to follow step by step. For using a computer, then this would be your Lego bricks as your input, your Lego houses as your solution, and the instruction manual would be your computer program. So a computer programmer has encoded rules for how to turn a bunch of Lego bricks into Lego houses. So then the machine learning approach is slightly different in that the computer will learn the instruction manual itself. So instead of a human going in and encoding rules into a computer program, the computer will learn what those rules are. And the way it does this is to learn through experience. So you will give the computer a lot of examples of your solution that you want it to produce, and it will learn how to get there from the inputs. So here's a simpler example. So let's say you wanted the computer to take some images of Lego constructions, and you want the computer to tell you what that Lego construction represents. So what you would do is you would gather lots of images of Lego constructions of different types, and you would go through and you would label these images with what you want what the output should be. So on the left, you would label this image as dinosaur, and on the right, you'd label it as penguin. And you would give all of these images and all of these labels to the computer, to the machine, and it would take the real labels, the answers, and the inputs with the images, and it would learn how to go from the inputs to the answers. So you don't only use images as inputs for machine learning, but you can use any data type. So you can also do the same thing with time series data, for example. So let's say you have a time series of sensor measurements, say from an engine or from a patient with wearable technology on, and you want the machine to classify certain parts of this data with certain behaviors. So let's say you have some engine failures, or you have some particular behaviors of your patient, and you want the machine to be able to tell you what they are from the data, so you don't have to have a human there constantly monitoring the data. So then you would go in and you would do the same thing. You would go and you would label your data with what you want the output to be, and you would feed these examples. You would gather many examples of this, and you would feed it into the machine, and it would learn how to go from the data, from these sensor values, to the answers that you want it to output. And it's not only classification, you can also use your labels to tell the machine when certain events happen. So you go in and you have an expert define certain events in your data, and you give this to the machine, and you can ask the machine to tell you when this will happen. So you can give it past data and where you know the time until a certain event, and then the machine will learn how to predict when this event will happen. And then you can give it new data, and it will be able to tell from the data when something is about to happen. And you can also ask the machine to learn how to predict future values as well. You can also use other types of data, not just time series data or images. You can use video, audio, or text, or genomic sequence data, and you can solve all sorts of problems by getting the machine to learn the rules from the data itself. So it will be able to learn the relevant patterns in the data to solve the problem. So then you don't need a human to figure out the rules and encode them into a computer program to solve the problem. You get the machine to do that for you. So that was a general introduction to machine learning. And now Christian will talk about why you would use, a little bit more about why you would use machine learning.
Yeah. So to talk about why you should use machine learning, it's not enough that it's just a cool thing. It has to bring some value. So to talk about that, we should talk about a buzzword that is often used. It's called data-driven decision making, which is often thrown around by marketing people as you know, oh yeah, you should make your data make decisions for you. And I don't like the term very much, because obviously everybody uses data to make decisions. Nobody runs a business today based only on feelings, and intuition. But the thing to discuss is how much data do you use and how structured are they? So let's look at some examples of different companies and the way they handle data. And abstract ideas of companies, I have to say. Let's first look at Bob. This is Bob, the icon. And Bob, he gathers information by talking to his coworkers. He Googles a little bit, and he makes some phone calls. So Bob has a very unstructured way of gathering data. It's only him, and he can only gather so much. So it's low volume. He can't do this very often because, you know, he also has a job to do. So it's low frequency. But our next guy, Charlie. Charlie, he is in a bigger company. They have started gathering data. They have a data warehouse. He gets his reports, the fixed reports. And he has structured reporting, so every day he can look at the same set of reports that he did yesterday. So it's higher volume. Unfortunately, when Charlie has an idea about how to change the data he views, he has to involve IT. He can't change the reports that he's looking on. And also, very often happens is that the data warehouse guys will gather a lot more data than they actually provide to the analyst. So Charlie can only view a very limited subset of what data is available. And if he wants to increase that, he has to talk again to IT, and it's a slow process to investigate and analyze data. Now, Alice, our next abstract analyst, she has gone further. She has now started with OLAP cubes. She has tabular models. She has Power BI. She has pivot tables, and she has the business intelligence suite. So what this gives to Alice is that she can access most of the data in the data warehouse by herself. She has dynamic reporting, so that she can, when she has an idea, oh, what is this? How does this data compare to each other? If we match this with this, what happens? What can I see? So she can make a lot more reporting and visualization and understanding of the idea by herself without involving IT. and she can view a higher volume of data. A lot of companies are here or have just progressed from the previous topic, and asked themselves, okay, where to move from this? Because there is no question that the data volume is increasing. So my data volume increases in every field. In industry, it's become very, very cheap to instrument, put sensors on machinery. For example, one ship engine can contain 500 different measurements that log information in 10 hertz or 100 hertz. So the data volume is extreme. There's a lot and lots of dimensions to handle, and human can only view so many at once. In banking, you have a lot of information about your customers. You have a lot of information of how they use your product now as things have become more digital. You have a lot of information about demographics in your area. So there's the ability to gather data has increased a lot, and the frequency and the volume of data has also increased. So you need more tools to handle all of this. In fact, you can make an argument that increased data volume without increasing your ability to analyze data actually just makes your ability to process data worse, because the analysts get confused and don't know which data to look at. And that's why we think machine learning is one way to progress from here. It's not the only way, but it is one way. So now we will talk a little bit of how to start a machine learning project.
Yeah, so if you are feeling quite overwhelmed with the volume of data that you have, and you don't know where to start to get the most value out of it, what we recommend is that you dedicate a few days, say 3 to 5 days, to do a data innovation sprint. So this is where you would gather all your key stakeholders in together. So your data scientists and engineers and decision makers and your domain experts, importantly. You gather them all together and you spend some time. So here we suggest a 3-day sprint where on the first day you would map out where you currently are with your data and how you use it and how it relates to your business goals. The second day you would then formulate solutions for how to get from where you are to where you want to be. And on the third day you would choose the best solutions and start making a concrete, detailed plan for how to proceed. So when we say taking stock, these are some of the questions we suggest you think about. So on the business side, you want to start at the end and think about where you want to be. So you think about what your vision is and what your goals are and how you might fail at these goals and how you measure your progress towards them. And then on the data side, you would map out exactly what data you collect and where from and how you store it and how everybody accesses the data. And you would look at what tools that you have for your data analysis or your data storage and what analytics you currently do. So you really take a detailed map of where you currently are and where you want to be. And then you can come up with a list of key business questions that you want to answer or problems that you want to solve. So then this provides a foundation for then going into the second day where you would brainstorm and come up with as many solutions as you can think of for how to answer those business questions. And on the third day, you would then choose the best ones. But after the first day, you would have this list of questions. And what you want to do to narrow down the list so that you know which ones to formulate solutions for is to map them out against two different axes. So business value on the Y here, and your ability to activate on the X. So you'll have some questions that you've come up with that you don't have much ability to activate on, and the questions actually provide very little business value. So those you would just exclude immediately. These are just curiosities. Then you might have questions that you have a high ability to activate on, but they still don't give much business value. So these are the incremental improvements. So you put those to the side for now. And the questions that have very high business value, but very low ability to activate on, these are your pipe dreams. So you would, again, you would leave them for now. And you would focus on this upper right quadrant, which is the questions that give you the most value and where you have a high ability to activate on. So you have these questions now categorized, and you take the ones in the highest value category, and you would rank them according to business value. And then you would pick the top 3. And then those top 3 questions you would then focus on for formulating these solutions on the next day of the sprint. And you would compare, you would take a look at how others have solved the problems before, and you would come up with all the ideas that you can think of to answer these questions. And at this stage is when you would think about how you could use, or whether you need machine learning. In some cases you might not, and in some cases you might get a lot of value from using machine learning to answer these questions. And then your decision makers would then decide which ones of those to focus on. And then you would take the vote on the best solutions and focus then on coming up with a concrete plan for implementing that solution. So I will talk a bit about how to plan a machine learning project, assuming that machine learning is part of the solution. But first, it's good before you plan to be aware of some of the peculiarities of the machine learning projects. So here is a very simplified flow chart for a machine learning project, but it is not as linear as this. So it's very important to keep in mind that when you're doing machine learning, you have to allow time for experimentation and iteration. But I'll go through the main steps. So here, the first step is to collect the data. So you might already have this data, in which case you would spend time selecting the data and figuring out what data is relevant to your question. And if you don't already have the data, then you will need to go out and collect the data. And once you have the data, then you need to clean it. And this is a task that is critical to the success of the project, and it's one that takes a lot longer than most people expect. But so this is when the iteration begins, because you might look at your data and you realize that the quality is not good enough. So you have to go back and start and collect more data. But once you've got enough data and you've managed to clean it up and it's high quality, you can begin training a machine learning algorithm. So you can select different algorithms and try different ones. And then you would take your resulting trained models and you would compare them and evaluate them and figure out whether they are doing what you want them to do. And at this point, again, you would have to iterate. So you might, the first model you train is probably not going to perform very well. So you will have to go back and tweak the model to make it better. You might also find when you evaluate the models that there's something in the data that you missed. So you have to go back and do some more data cleaning. You might even find that the data that you have isn't enough. So you would go back and collect more data. But let's say that your model performs well, then you would test it on an independent subset of your data that the model hasn't seen during training, so it hasn't learned from. And this is to check that it performs well on new data. And at that stage, again, you might find that that it doesn't, and you need, and usually that means you need to go and collect more data, because when you trained, you sort of overfit to the training set, and you don't have enough examples in your training set to cover everything that happens in the real world. So you'll have to go back and collect more data and start the cycle again, because every time you collect more data, you will have to then clean it and check it and repeat the training and the evaluation. But if the model passes your tests, then you would go ahead and deploy it into production. And then the cycle doesn't end there. So it's very important that you monitor a deployed model to check that the performance is what you expect after you've deployed it, and also that the performance of the model stays at a sufficiently high level. And if the model is not performing as well, so over time, the model performance can deteriorate because your data may change over time. And so at that point, again, you would have to go back and do your evaluation of the model, and perhaps go back and collect more data or do some more data cleaning, or usually it's retraining on newer data. So with this cyclical life cycle in mind, I've mapped it out here on a linear timeline. But this is a generic timeline, and it's simplified. So your particular project will, the timeline will look different. It depends on what you already have in place and what the nature of the problem you're trying to solve is. But in general, these are the blocks of time you'll need to allocate for each part of the project. So for the life cycle of the project, the machine learning life cycle, you have your data collection at the top, and this can take a lot of time. And usually it's a continuous process, so you're always collecting new data, but you will need to collect enough data to start with to train a decent model. So you will have to allocate plenty of time for that, and not just data collection, but also labeling the data if you have a task that you need labeled data for, and that can take a lot of time. Then you have the data cleaning underneath that, and that can start as soon as you get a sample of data. You should look at the data and check the data and get to know the data and what issues the data might have, and start developing pipelines for cleaning the data. And then you have the train, evaluate, test, deploy, and monitor down here. And I'll always allow some extra time for iterating. So going back and retraining, or going back and cleaning the data again. And this iteration is variable depending on the quality of the data and the complexity of the task. And then at the end here, you have a block of time that you need to set aside for improving the model. So once you've deployed it, you might want to improve it continuously, or retrain it if the performance is deteriorating. But aside from the machine learning lifecycle itself, you have lots of other tasks that you have to do. So if you don't already have it in place, you need to set up infrastructure, and this can take quite a long time, depending on what you already have in place. So you need infrastructure for your data collection and storage, and also for the machine learning lifecycle itself. And you need to set aside time to integrate the machine learning into your existing system. And also you should always allow some time to automate the machine learning lifecycle. So once you've done one pass through the machine learning lifecycle and you've deployed a model, you want to have something in place where you can automate the model updates. So automate checking that the model is performing well, and automate retraining if it's not. And you need to make sure you have time to develop pipelines that can be automated. Then you have some time for prototyping at the beginning. So it's quite useful to not wait until you have all of your data, but just build something simple which you can figure out what it is that your model needs as the inputs, what it should output, and how it will integrate with your existing system. So you can do that right at the beginning. You don't need so much data for that. You just need to know what your data will look like. And then you should always allow time for refactoring and documentation. And I would always recommend right at the beginning, before you even collect the data, to have a block of time for planning the project. So as well as the data sprint, I would always have some time where you can sit down with the domain experts and the data scientists and figure out exactly what you want the model to do and how you will judge how well it's doing in production and how well it's doing at answering your question that you set out to answer. And these should be quantitative. So you should always figure out at the beginning exactly what metric you want to use and a numerical value for what is what defines your success, so that you can use this to evaluate the models. So that's a bit about how to do machine learning, how to plan machine learning. So now we will move on to what not to do. In our experience, we've seen many examples of pitfalls that people fall into, which can be harmful to the project, the success of the project. And some of these, if you get stuck, it will mean that your project will certainly fail. So we will go through these top ones. So the first one, which is one of the most common ones we see, is that the goal of the project is not well defined. So it's not enough to say that you want to solve this problem and you want machine learning to do it. You need to be concrete about what you want, and it has to be translatable into some quantitative numerical values. So you need to decide exactly what you want your model to output. So if it's a model that's going to do a classification task, you need to decide exactly what classes you want to use. And you also need to decide exactly how you use the output for the model and what you want that output to look like. So if it's classification, do you want the model to output the one class? You want it to tell you which class this data that you give it is? Or do you want it to output a probability of all the different classes that you have, for example? And similarly, you should define exactly what the inputs of the model should be. So it's very important to work with domain experts for this. So they have the most knowledge of the data, and they will be able to help the data scientists to figure out what data is most relevant to the problem and exactly what you should give the model to learn from. And then again, you have to define exactly how you'll measure success. So what metric will you use? If you have more than one metric, you need to figure out how to combine them so that you have one numerical value to assess your project against. And if you have some criteria that need to be met, those need to be well defined with numerical values. And again, you need to define what success means. So against these metrics of success. So whether this should be a threshold on your metric for success. So you need a number. So if the performance of the model goes above this number, then you've succeeded, and that's when you will deploy to production. So it's very easy, if the goal is vague, it's very easy to first of all solve a completely different problem. You might have a fantastic model that answers a completely different question, or you will end up spending months and months of time perfecting a model and getting it to perform that much better when you already had a model that was good enough weeks ago, right? So you need to have all this set out ahead of time so that you don't waste time.
Yeah, so next, the pitfall we have is that if you don't have a clear plan for how to use your final result. So the final result of machine learning data scientist part of it is to create a model that analyzes data and gives an output. But how will you need to have a plan for how the end user will use this output. How will he view it is very important in the sense that if you generate just an extra web page where there are some more information, it will often be overlooked by your analysts. So you have to integrate this into the existing systems that they already use today. This can take time. And it is important from the beginning to have an idea of how to automate the models. So you so all the work that the data scientists do during the discovery phase and building of the model needs to be automated for the model to work. So you need to have an idea of how this will implement, what architecture to use, what the data flow will be to the model, and how the model will be deployed. Without this, you will just end up with a model in a drawer somewhere, and it will only provide value very initially. Yeah. So, and another common pitfall that I have seen in several projects is that you don't prepare your organization what to expect from a machine learning project. The issue often is that machine learning has sort of a quite odd view when it's presented in media as some sort of robotic takeover, that the machines will come and do everybody's job. And humans have an idea that, well, I don't want to be replaced. So if you don't spread information, the idea, if you don't sell this to your organization in the correct way, you can end up with human experts that don't want your project to succeed, and they will not be engaged in helping your project succeed. And domain knowledge is critical in any machine learning project. So if you go into this without preparing the people, that this project will actually provide tools that can help the human experts to do a better job than they do today. So it will just be another tool. It will not replace anybody. Then this will fail. So I've seen this several times where we have struggled against this idea that, you know, if this project is successful, then I will lose my job kind of thinking, which is almost never the case. It's very, very hard to make a machine learning project that actually replaces a human expert. And it's much more easy and much more likely that you will make a tool that can give the human expert an ability to process more data and make better and more informed decisions. So, yeah.
Yeah, so related to this is the next pitfall, underestimating the importance of the labeling process. So high quality labels are critical to the success of a machine learning project if the labels are required to solve the task. And it's one of the common problems is that some of the data are labeled incorrectly. So let's say you have the task of training a model to classify pictures of fruit, and you get somebody to go in and you label all the images with what type of fruit they represent. And let's say there was, in some cases, somebody has gone and mistaken apples and oranges, so they've labeled some oranges as apples. Then if you give this data to the machine learning algorithm, then once it's trained, it will actually be confused about what is an apple and what is an orange, because it's got some images of apples that are labeled correctly, some images of orange that are labeled correctly, but then some that are mislabeled. So it can't learn which one is which. So this is a very common problem. And if you can ensure that this firstly doesn't happen, or if it does happen, that you're able to fix it, then your model will be much more likely to succeed. Another problem is that the training data, it has to reflect the data that your model will actually run on in the real world. So a problem is that if you gather some training data and it just doesn't reflect the real world. So for example, if you back to this fruit classification task, if you take only images of apples when they have a green background, like these two images here, and you only use those type of images to train your model how to recognize apples, and then you deploy your model and you want to give it an image of an apple hanging from a tree, it will probably not recognize that that is an apple. Whereas if you had given it lots of images of apples hanging in trees, then it would have done a much better job. So getting correct labels and getting enough that cover all possible scenarios that you can think of that the model will see in the real world is very important. And in the case of labeling different types of fruit, this is a relatively easy task. But in most cases, it's a bit more complicated than that. So let's say instead of just classifying different types of fruit, you actually want to classify apple varieties. And then you need somebody who can recognize, when they're doing the labeling for the training data, they need to be able to recognize these different varieties of apples. And so that requires more knowledge than most people have. This gets more and more difficult with more and more complex problems. And then you need more and more expertise from the person that's actually doing the labeling. So in most cases, the data scientist doesn't have this domain expertise, and the people labeling the data should have this knowledge. So in most cases, the domain experts are the ones that should be labeling the data because they have the most knowledge, so they can produce the highest quality labels. They won't make so many mistakes, and they will know what examples the machine needs to cover all possible situations in the real world that the domain expert can think of. And usually the data scientist just doesn't have this knowledge. But the problem with labeling is that it can be very tedious and extremely time consuming. And usually it's not a task that most domain experts want to do. So this is made even worse if the domain experts think that the model is going to replace them, as Christian talked about. But even if they are excited about the project and they want the project to succeed, it's not an appealing task for most domain experts. And especially when you have highly complex data, they will need to spend a lot of time to go in and do this accurate labeling. So it's really important to make the labeling process as easy as possible. So you should standardize the process, and you should make it very clear what you want the domain experts to do, and you should make it as easy for them to actually do it as possible. So there are existing tools that you can use to help people label data. And most of the major cloud platforms will have some labeling project capabilities. But you might, if you have unusual data types, you might end up having to create your own custom labeling tool. But the most important thing is to be aware of is that you have to do this for the project to succeed. Otherwise, it will be a huge bottleneck because you just won't have the data to train your model.
Yeah, so the next common pitfall is an incorrect allocation of resources. So it's often easy to view the machine learning project as something a data scientist do, but there is actually several other roles that go into this. You have the domain expert that we have talked about that need to label data, but also help the data scientist to evaluate models, to explore the data, define goals. And it's very, very important that you as a manager, when you start a machine learning project, give the domain expert dedicated time to participate in the project. It is not enough that you just say, oh yeah, they will help you when they can, or they should help you when you need. You need to dedicate some percentage of their working time to participate in this project. Otherwise, these people are the domain experts and knowledge experts in your company. They will be busy with other things, and the data scientists will not get enough information to do a proper job, and your project will fail. And also, another common mistake is to underestimate the data engineering part. So moving the data, storing the data, cleaning the data, automating. This is much more often, in my experience, a much bigger task than the actual data scientist bit. So you need to make sure that when you start the project, that either you have a guy to do the data engineering, or you make sure that the data scientists have this knowledge, because not all data scientists are data engineers, and not all data engineers are data scientists. It is possible to wear both hats, but make sure that the data scientist have, if this is the only one you have, and he's going to run most of the project, that he has knowledge about architecture and moving data, storing data, and deploying models. If not, you need to expand your team or provide more training to the data scientists before you start. Otherwise, your project will fail because the architecture will be very poor, and you will run into a long set of problems. So yeah, the next pitfall.
Yeah, so one of the most common pitfalls is not checking the data enough, or at all in some cases. So you always need to make sure that you get to know the data that you're going to train a model on. You need to make sure you clean it thoroughly. So things that you should always check for are missing values and extreme values. You should also look for unexpected patterns or correlations and unexpected distributions in your data. So this is, again, where domain expertise is required. So a domain expert will be able to tell the data scientist what the data should look like and what correlations in the data should be there or should not be there. And if there are any outliers, then the domain expert will be able to tell the data scientist whether that's normal or not. And then you need to deal with these things before you train the model. So it's especially important for machine learning because in most cases, if you have missing values, then the model will just, the machine learning algorithm will just, it just won't train, it will fail. So that's at the training stage, but also it's very important once you've deployed your model to make sure that all these checks are done on any data that that model receives in production. So you should always clean the data again before the model receives it. So the same cleaning process and pipeline you use to clean the training data should be done on the data that the model gets once it's deployed. Because again, if it receives missing values, then it will just fail. And also you should be, you should set up some kind of monitoring and alerting system where if these things do come up in the data once the model's deployed, like suddenly you have missing values where you didn't before, you should have an alert that for somebody to go and investigate, because it will cause the model to stop running, and it would probably indicate that there's something wrong in the data collection or the data itself. So for example, if you have a set of sensors and your model relies on a certain set of sensors, and suddenly one sensor gives lots of missing values, the model won't run. And if this is not checked, then you can go for weeks where the model's not generating any outputs and there's something wrong. So usually it means that one of the sensors has failed. So you should have something in place to check it out and fix it so that the model can continue running. And our last pitfall is that in a lot of cases, people are very optimistic when it comes to time estimates for machine learning projects. So most people, when they think of a machine learning project, will just think of the model training and maybe the evaluation and deployment. But there are all these other tasks that you have to allocate time for to support the machine learning. So you should always allow time for defining the goal and for planning how you're going to use the model in the end and how you're going to measure the success. But as well as that, you need to make sure you set aside enough time for setting up infrastructure, set aside plenty of time for labeling data, and not just the labeling itself, but setting up the tools for the labeling and designing the process for the labeling. Then you need to make sure you allocate plenty of time for data exploration and cleaning, both for the data scientist and the domain expert. And you should also allocate some time for figuring out, as you're collecting the data, when you have enough data to have a model that's good enough. So you can, as the data come in, you can train a model and record its performance, and you do this for when you get new data, you retrain on a higher volume of data and you track the performance, and once the performance starts to level out, then you know you have enough. But this takes a bit of time to implement, so you should allow time for that. And then always allow time for optimizing a model. So this iteration of the machine learning lifecycle takes time, and the more complex the task, the longer this takes. And then again, integrating the models into the existing system, you have to allow time for that. And always for documentation and refactoring code should be time allowed for that too.
Yeah, so then we come to our summary slide, how not to fail at machine learning. So this is certainly things that you should do. It's not a guarantee for success, but it will at least avoid some common pitfall. So you need to have a well-defined goal. You need to create a plan for how to use the final result. Prepare your organization. Allocate resources, human resources, to cover all aspects of the project, which is maybe broader than you expect. You have to involve domain experts early and often, and make sure that they have the time to do this. Don't underestimate the data labeling. Make it easy to label. And again, you have to sell this to your domain experts, that this is very, very important for the project to succeed. Have quality control of the data throughout the project, both when you are doing the exploratory part and also especially, I guess, in the end, automated results, automated pipeline in the end, and allow enough time for all the stages of the project process. It doesn't need to take a very long time to make a machine learning project, but it also can't be done very, very quickly. So that is it, really. Thank you for listening, for everybody who stayed to the end. We can take some questions.
Questions, Christian.
Oh, exciting.
Yeah, Tomas is wondering, finding the best machine learning algorithm may be a trivial job for an expert. However, complexity and runtime analysis of an algorithm should always be discussed and taken into account. Any viewpoints?
Yeah, it's sort of a two-part thing, this, because we have to talk about the complexity and runtime when we are discovering the model, and then it is very variable how much time, how long time, or how complex it takes for an algorithm to train on a data set. A deep learning model can use hours and hours to train on what an XGBoost decision tree model can do in seconds. So it is interesting often interesting to choose a faster training model test and discover data, and then deploy a deep learning type thing that maybe will produce a stronger result later on in the project. Because then, if you start with a deep learning thing, you can spend a lot of time simply just waiting for things. So instead, use something easier and faster early in this discovery, and then you also have to discuss, okay, how fast does this model need to be? I have projects where we need to deliver a result in a second, and I have projects where it is okay if we deliver a result every 20 minutes. And of course, then in the 20-minute case, you don't need to have so much focus that your end model need to predict very fast. It doesn't need to run fast. If it spends 2 minutes to calculate the answer, that's completely fine, because then you have 18 minutes left to do, left to spend on other things. But if you need to provide everything within seconds, then you need to pick models that will actually run fast too. So it's my viewpoint is that it depends a lot on the project and end use goal of what you're doing.
Thank you. And then the second question we have is classification models will always provide a result. Can you say something about how to detect high uncertainty in the prediction?
Yeah, so usually with a classification model, you will output a probability for each class. So you can have a look at those. And if the model is very certain, it will give you a high value for the class for a particular, it'll either give you a very low value or a very high value. So it's either very certain that it's not that particular class, or it's very certain that it is that particular class if it's close to 1. And then it'll have something in the middle. If the model is uncertain, it will give a probability of around 0.5. It's not sure if this is the class or not, if it's if it's just 2 classes, or if it's multiple classes, you'll have all the classes will have a very similar probability. So that's how you can have a look at the uncertainty, and you can plot this as a heat map. It's quite useful to get an overview of what the model is, sort of the certainty of the model if you plot this as a heat map. So for different examples, you can plot the probability for different classes and see where the model is most uncertain. And actually, it's very informative to do that, because then you can see, okay, for certain classes, it's just very unsure all the time. Whereas for some classes, it's very easy for the model to know that it's that class. Yeah, that's the way I would do it.
There is someone else who said something more. If all the specification must be so strict in a machine learning project, then how can it be more flexible than the static reports which use common programming?
Well, the end model is often not very flexible in the sense that it has a certain set of data inputs that need to be in place for it to predict some sort of result. But when you select those inputs, you have an opportunity to analyze the data in a way that you can try to pick out which of these inputs will provide a value. And in the discovery phase of the machine learning project, you will discover which of your data points is actually important and which are not. And this is something that in theory, a human analyst can do, and then provide a rule set to the common programmer to implement. But it can be very, very hard for a human to view many dimensions at once and learn and discover knowledge and information when you view multidimensional data with very high dimensions, which machine learning allows you or helps you to do. Yeah, but if the amount of dimensions is low, you can easily create, well, not easily, but the analyst can help create a rule-based system and use common programming, as you say, to create a tool. And of course, this is a very common way to create expert systems. The thing is that as the dimensionality of the data grows, the complexity of the rules you need to implement grows and grows, often exponentially. And in the end, the quality of the rule-based system that you are implementing might deteriorate as the dimensionality increases. Yeah.
Perfect. Thank you so much. And thank you everybody for joining us today. We will send out the presentation afterwards, or the recording of this presentation, so you can view it several times if you need less speed in the presentation. We have just reached the clock of 11, so thank you all, and join us next time, hopefully, and please give us feedback if there is anything you want to share. Okay, bye-bye. Have a great day, all of you. And thank you, Christian and Gemma.
Bye.
Bye-bye.
Bye-bye.